So hello all together. Thanks for joining us today for today's meetup. I also welcome Sasha Schubert, who will be the one to present this evening. Happy to have you here, Sasha. Welcome.
Thank you very much. Good evening, everyone. Good morning, good afternoon, wherever you are.
I guess it could be everything from the
It's a
evening.
virtual world, isn't it?
It's absolutely virtual here. Yeah, thanks all for joining. Just the typical remarks when before we start here, as always. You know that this kind of webinar tool software from Zoom allows you to ask questions. So if you look down to your navigation bar, there's a part where you can ask questions, Q&A. I will do my very best to check what kinds of questions might come up during the presentation. I will also ask Sasha the questions during the presentations, so we don't wait until the end. He's an absolute professional, and I'm absolutely sure that this will not confuse him in any ways. So feel free to ask your questions at any time when you think something was not really understood, or you have a feeling that there might be something you need to get or want to get a little bit deeper into it. Yeah, so today, coming back to what's the topic of today, we want to have a look at AutoML, and it's actually about how to reduce time to model, right, Sasha?
That's correct.
Thanks. Thanks for the confirmation. I wasn't really sure, but I think we are on track. I was very curious about you and yourself. So as we had a little discussion before we started, I would like to know a little bit about you and your background. So you have some links to weather, right?
That's right. Yeah, that's right. So, yeah, I have a slide in my presentation, but let's chat about this right now. My background: I've been with SAS, the company, for more than 20 years now. I started doing statistical modeling, predictive modeling in the 80s, in the end of the 80s, and joined SAS in the 90s. And my academic background is actually weather forecasting, meteorology. So that's where I kind of got to know statistics. I use statistics to verify the predictions of weather forecast models. So that's where I started. And then after doing a PhD in that area and working in academia, I kind of moved over to not predicting the weather, but predicting human behavior, really. So I started applying predictive modeling to customer behavior modeling. So trying to predict, that was the time of customer relationship management when that started. So my first projects were about predicting what customers would react to, what kind of offers companies would send out, if they would buy, if they would leave the company, if they would cancel service. So all the traditional customer relationship management models. And from the beginning, I was involved in applying SaaS technology to these kind of business questions and business problems. So predictive modeling, and then it moved through the times, which were really interesting, and became even more focused on using analytics for all kinds of business problems, if you want. I moved into maybe also using predictive modeling for fraud detection, predictive modeling for supply chain predictions, all kind of things where with the digital age and companies figuring out that there's digital data everywhere, there's electronic data everywhere that can be used to analyze what's going on, and then use predictive modeling to maybe have a little glance into the future and trying to make better decisions based on data analysis and statistical algorithms. And now we're in the times of artificial intelligence, right? And we're not only talking about using the results of a model as a decision support, but we're moving into the time of using the results of a model for automated decision making, which is really, really interesting, and maybe for some people even scary, right? So we will have self-driving cars probably in the future. We'll have self-driving planes, self-driving everything. And so I would have never imagined when I started in this area that we would develop into that kind of direction. It was really interesting and challenging both at the same time.
Quite interesting insight. So because you have that kind of huge knowledge about so long time, about what has changed, do you think the challenges for data scientists of engineer, who is working in that field, has changed substantially from the past?
Definitely.
today?
Definitely it has. I mean, I used to be, it was when I had my first project, I still remember, it was more like, oh, we came in and they said, okay, there's your corner office. You would sit in that office and you would analyze the data, and at the end of your project, you would present the results to someone, and they would say, yeah, interesting. Let's see what we can do with this. And now it's much more ingrained, much more integrated into business processes. And we have organizations that run maybe not the entire business yet, but large parts of their business on automated processes and automated decision making. So the data scientist these days is much more integrated and involved in the project, in those change projects, if you want, because it's not only about predictive modeling. Of course, it's about changing business processes and making business processes more intelligent, more automated, and faster. And so there's a whole, and I will talk about that in my presentation a little bit as well. There's a whole end-to-end life cycle that we look at these days, where lots of different kinds of users are involved, not only the data scientist, but a data engineer, an application developer, an IT person, and bring all these people together and working in an agile and integrated collaborative way. I think that's one of the challenges, but also one of the nice parts of the jobs these days.
Yeah, interesting, very interesting. Looking at what, if you're talking about predictions, does it have to do something which we will cover today as well? Is predictive engineering something a subject for today?
Yeah, I will kind of focus on, or kind of, yeah, I have a big part of my presentation is about how to help data scientists becoming faster, more productive, and maybe also more accurate. So coming to the point where you say, hey, I analyzed this data, I applied my algorithms, and I'm now confident that this is the best model I can build. And the model is also useful, so it can help to make better decisions, because decisions are not based on subjective um, judgments, but they're based on objective data analysis. And then the second part will be a little bit about helping data scientists and data engineers and application developers as well to put the models into a business process, integrate it, and actually apply the model and generate value from the model, and make sure that your model that is in production is generating value, not for a short time, but over a long period.
Interesting. Sasha, I just conducted a quick survey here among the people attending today, and actually asked if they could describe a level of knowledge and experience with machine learning. And here's the outcome for you, maybe also interesting because you can focus a little bit.
Right.
People new to the field are about 1/5 of the participants today, so 19%. Advanced and experts. Advanced and expert are the major parts. So advanced about 52% of the majority, and experts 29%.
Okay.
So I think for just for the audience here, if you are really new to the field, don't worry. Ask your questions. We always welcome questions. Don't feel silly or something like that. If you're just struggling with something, ask. And for the rest, yes, of course. I hope you have a lot of questions today. And I'm really looking forward to the presentation of Sasha. Sasha, I would like to invite you to take the floor and introduce us to the subject of today.
Okay, I will. So I will share my screen. And let me know when you can see the slides.
Yeah, I see the presentation already, so that's fine.
Okay, let me start the presentation.
Yeah, it's
Okay,
it's
great.
it's Retina view. Yeah, so it's not the public presentation. It's your view actually. I can see.
It's what?
It's not the public view. It's a Redner Notizen. You can see it's the Redner view.
Okay, so I have to change the I see.
The mode.
Changed. Yeah, let me change that and bring it over here. I have two monitors.
Oh, fantastic. Okay.
Okay, can you see the slides now?
I can see the slides still, but I see also the preview.
Also the preview. Okay, then I have to stop this and probably view. Where's the monitor? Sorry for that. We didn't have that before, did we?
No, maybe it was the wrong screen. I mean, it doesn't matter. It's just yeah, we see more from the next.
So you have two windows, or what's going on?
No, I see the presentation. I see the preview of the speaker, not the preview of the audience.
So what happens if I change? If I do this? Still the presenter's view?
No, I see the presentation, the PowerPoint.
Yeah, now you see the presentation.
I see the presentation. I see just the open PowerPoint. Software.
Okay, cool. So now we can start.
Can you just go into presentation mode?
I just did that. That's weird. That's really weird.
I think it's not so bad.
Why is it not?
It says, please duplicate your settings, go to your display settings and select duplicate view. Thanks for the help from the audience. Hey, guys, you're awesome.
What's that? Duplicate view?
Go to presentation mode. It's okay. I can still see the preview of the next slide, but I think it doesn't matter. No worries.
Yeah. Oh, it's up here. I think I know. I think what I know what he means now. Let me. Where's my mouse? I go over here, display setting, duplicate slideshow.
Yes.
Can you now see the slide?
That's perfect.
Okay, that's what he meant. Thank you for the support. And let's
Unity, I love it.
Let's start. Yeah. Okay. So what I would like to talk about today is automating machine learning, how you can use automated algorithms, automated tasks to do certain steps in a machine learning pipeline quicker and hopefully also more accurate. I talked about myself already a little bit. So if you want to connect, I have a profile on LinkedIn. I put the link in here in the slides. You can probably also find me if you search on LinkedIn for my name and SAS, and then connect if you want to, and we can kind of have a discussion after this presentation, or if you want to reach out and discuss other things, feel free to do that as well. What I want to touch on today is these three topics, basically automation of machine learning and what we mean by that and where this is coming from. Then the key steps of a machine learning pipeline and what can be automated in those key steps of a machine learning pipeline, and how does it help, how that helps a data scientist to become more productive. And then I want to also talk about a little bit about automating model ops. So model ops is a new framework, or it's not a new framework, but it's become a little bit more of a hot topic of discussion lately, where we're talking about not how to develop a model, so how to apply a statistical algorithm to data and create an algorithm that can predict an event or a certain outcome on new data, but how you actually put that model that you developed into production, put it into an application and use it for regular results or regular answers if you want. So might be kind of a real-time application or application on a mobile device, or might be a process in your organization where whenever something happens, a model runs in the background and provides an answer, and that answer, based on that answer or that the result, a decision is taken. And there we see a lot of potential for automating certain steps as well in that part of what we call the analytical lifecycle. And hopefully at the end we'll also have some time for question and answers, but feel free, as Stefan said, to jump in at any time. And even if we don't finish the presentation, we'd rather kind of address your questions than going through the slides. So when people think about automating or automated processes, automated machine learning, often they think about the end result. So I talked about what I say, kind of what I call model deployment a little bit already. And the model deployment really is the part where you have a certain process, and as part of this process, you have a model involved, and that model is doing certain things automatically. So for instance, we have our speech recognition devices, so Amazon Echo or your assistant on your mobile device. And what happens when you speak to that device is actually it takes the sound and it turns the sound into text, and then it analyzes that text and provides an answer. So there's a model involved in doing that. Similar to manufacturing processes that is kind of shown here on the top left hand corner, where you might have a manufacturing process, an assembly line, and then you might have cameras that monitor this assembly line and identify issues with the quality of the product that's being produced. And automatically, when something happens with the product, when they identify an issue, they create an alert, and based on that alert, some action is taken. So again, in the background, there might be a model running, analyzing the images that come from cameras or sensors, data that's coming from sensors, and automatically identifying something that needs to be actioned on. Or you get I talked about self-driving cars, or you get a message when you walk through a shopping center that just the shop you walk by has a special offer and makes a special offer right on your mobile device when you walk by. All these kind of things, automated processes where organizations are using machine learning in the background to analyze the incoming data and then make certain decisions and take actions based on the output of a model. But when we look at the automation that I want to talk about today, it's not the automated process at the end of a machine learning pipeline, if you want, where we have a traditional process that creates certain types of data from sensors, from cameras, and so on. Then you have an artificial intelligence, machine learning, black box, where you have certain models, and then that is fed into the automated process that I just talked about. But I really want to talk about the automation within that box here in the middle, where we create the model that then helps to drive and steer this automated process on the right-hand side. And that's called basically automating machine learning. So there's a nice article on Forbes.com from a guy called Janakira, and he talks about a traditional machine learning workflow where you have several steps, and everybody of you who's been involved in machine learning knows these kind of steps. Some people call it model lifecycle, some people call it a machine learning pipeline, but basically the steps are always the same, and they're listed here, that you go from data acquisition over data exploration, data preparation, feature engineering, model selection, model training, hyperparameter tuning to predictions. And within all these steps, there's a lot of work involved to create an output in that box that is the optimal input for the next box. And traditionally, many of these boxes have been manual work. Over time, of course, the data scientist usually writes code, and then that code obviously can be used to automate some of these boxes. But basically, when we talk about auto machine learning workflows, is that you have some data and you provide that data to that machine learning pipeline, and then the machine learning pipeline can run, doesn't necessarily have to, but can run automatically and create your prediction. So all these steps inside are done or can be done automatically. Obviously, there needs to be a lot of guidance, a lot of policy, a lot of constraints and steering within those boxes to make sure that the results that are created are useful and can help to automate and accelerate that process. And I want to say right from the beginning, when we talk about automated machine learning from a SaaS perspective, is we're not saying we want to create a black box, right? It's not that, even though on this slide these boxes are grayed out, from our perspective, that does not mean you cannot access those boxes and you are at the mercy of the machine, and whatever the machine tells you is what you need to take. It's really that you get a kind of a quick start, you get a very fast answer from your automated machine learning pipeline, And that might be something that you're happy with. And if you're not happy with that, you can open all these gray boxes and go in there and customize and improve what's going on there with your own insight and your own customization of those boxes. But basically, that's what I want to talk about in the first part of my presentation, is what's known as this kind of machine learning pipeline and how you can apply automation and furthermore intelligent automation to these, some of these boxes. I won't go through all of them, but some of these boxes that are listed here on this slide as part of that pipeline. So first of all, obviously, is data pre-processing. And we all know, even though we already have kind of very highly specialized algorithms that we can use these days, especially when we talk about artificial intelligence, very, very complex neural networks for image processing and natural language processing. But in every project starts with the data, and I haven't seen a project yet where there was not a problem with the data. And so the pre-screening or the pre-processing of the data, how much can be automated here is always a question of debate. But I think there's a lot of things that can be done with the help of the machine to identify, first of all, identify issues, quality issues. Secondly, provide suggestions of how to fix these issues. And thirdly, when the issue has been fixed, to identify if the fixed variable that has where we have the quality issues removed is a better predictor than the original one, and should be used in our model instead of the original raw data. And there's lots of things you can do, class and numeric variables, you know, look at missing values, look at the number of levels, and identify first of all, what should be done with those variables. Should they be used as a class or a numeric variable based on the number of levels? What happens if I have too many missing values in my variable? Should I still, if I have more than 60% missing values, should I still use that variable, or should I kind of apply an intelligent algorithm to replace the missing values? Should I just use the non-missing values? All these questions a data scientist needs to answer, and obviously automation and intelligence in the background of that automation can help to answer those questions and fix the issues. And basically the next step from that is automated feature generation. So I have my raw variables, and I get maybe a lot of things that I could have a look at and need to look at to identify what to do with those raw variables. Can I use them as is? Do I need to apply transformations? Do I need to apply fixes? And I have listed a few things here that are kind of provided usually with automated feature generation tools. So look at high cardinality. If we have a level and a variable that has many, many levels, might it be postcodes or might it be regions in a country? Can we identify natural groups in there? Usually many users look at high cardinality and maybe group neighboring levels. So if you have like 1 to 20, I might go from 1 to 5, and I might go from 6 to 8, and so on. And that's kind of a traditional way, but you could also look at the relationship of each level to the target and identify groups or levels that have very similar relationships, and then group those rather than kind of going by artificially introduced boundaries in your data. And all these other things, statistical parameters, high kurtosis and skewness, outliers. You can apply automated algorithms that might be based on one hand side on policies. So a policy might be, okay, I have a distribution here, give me like the percentiles or give me the quartiles, and then group my data by those boundaries in my distribution. Or I might look at kind of a more automated, intelligent way of fixing those issues. As I said, looking at the relationship to the target, looking at the best optimal transformation. And a big issue often, especially when you as a data scientist deal with a lot of data, and usually there's no shortage in data these days when you start on a predictive modeling project, you have dozens, maybe sometimes hundreds or thousands of variables you could use in your project. And when you have these many variables, usually you run into the problem of collinearity. So there's dependencies between the features that might obscure your modeling results, and identify those dependencies and fix them automatically again is a nice area where the automation can help the data scientists to make a decision quickly and clean the data. And obviously, as I already said, it's kind of the challenges here really is the input variable screening to define which features I should transform based on data quality thresholds, based on collinearity, based on statistical parameters that don't fit my model prerequisites, my model constraints, and then feature selection, define which new features I should select based on the feature target relationship. And as I said, often these days, data scientists deal with lots and lots of variable only in their raw data. So if you have like 100 variables in your raw data, and then you, based on the automation, you create new features, you might end up with twice, 3 times, or 10 times that number of features that you have generated from your raw data by applying all these fixes. And which set of those features you should now actually use in your modeling project is something, again, where automation can help you. And then automated feature transformation is on top of your raw variables and your generated features. You might also want to go into combining features, especially if they are related to each other, and creating new combinations of those features. And many of you that have been in this field for a while are familiar with transformations like principal component analysis, single vector decomposition, but maybe also with kind of the more kind of a more newer type of transformation, which is called autoencoder. And I have a little graphic here. Basically, an autoencoder is a way of doing a nonlinear transformation of your raw variables into new combined factors, which is nice because principal component analysis and single vector decomposition can only do a linear transformation. So you might, with an autoencoder, keep in your transformed features even nonlinear relationship between your input variables, and that's a nice way of compressing your input feature space from maybe a couple of hundreds to a couple of dozen, or even in the single digit, without losing a lot of information. And so these autoencoders have become quite popular in the recent past of doing that feature transformation rather than using kind of linear methods. And then data exploration. Everybody does their own data exploration, I'm sure. And usually what you do here is you create visualizations to identify relationships in your data, to identify statistical characteristics. And what you can also do maybe is kind of run just an automated algorithm, like it's shown here on that slide, that provides you with the insight into the input target relationship. Obviously, you don't want to have hundreds and hundreds of input variables, input features here. But if you have kind of a manageable number, you can just throw them into this exploration algorithm, and it will come back with something like this, which is an interactive report. You can click in here and you can identify for each input feature that is listed on the left-hand side with these kind of colored bars here, what is the relationship to the target? And they're also ranked by their potential or their power to predict. So what the one at the top has the closest or the strongest relationship to the target. And down here at the bottom, you can even get kind of a description of the relationship, where artificial intelligence is used to create that description. So natural language processing is used to use the statistical numbers that are coming out of that exploration of that analysis, and then it's put into some kind of more understandable language to see what is really the relationship between that specific variable here and that specific segment of that variable to the target. Obviously, we get some visualizations as well that make it easy to understand what's going on.
Sasha, can I ask a quick question?
Sure.
You can just go back for a second.
Yes.
Just for all those who haven't heard about that before, can you explain what Net Promoter Score is?
Right. Okay. Net Promoter Score is a way of analyzing the sentiment or the attitude of a person towards an organization or the service or products that organization provides. So basically, I mean, you see that quite often when you use a service online and the service has been provided to you. At the end, they ask you, how likely are you to suggest or recommend that product or that service to someone else? And you have usually kind of a rank between 1 to 10. And based on these numbers, you can calculate a net promoter score and then see how likely or how satisfied are people with your product or your service that you provide. And obviously then you can produce that for predictive modeling to identify people that you might want to use in your marketing campaigns to do the marketing for you, because they're really promoters of your services and products. That's the idea behind the net promoter score.
So isn't it a kind of API I can use?
It's not an API, it's kind of a concept of identifying people that have a high affinity to your products and services, so that are likely to buy again, but also likely to recommend your products and services to other people.
Thank you.
It's a marketing concept. Okay, and then we move into building our model. So we have now prepared our data. We have transformed the data in a way that is the optimal way of the model to digest that information that's coming in and turn that information into a formula or a recipe to make predictions. And here you need some input. Obviously, you have what we call in this case the analytical base table, which is that final product of your data pre-processing step. You have some parameters for the model that you need to set. Might it be a decision tree or might it be a gradient boosting? And you have some assessment matrix. How do I define if the model is a good one or not? That comes out of my modeling, the model development. And then I feed all these ingredients basically into my model template, and then the model template runs and creates a model, and I can then identify based on the assessment matrix of if the model is any good or not. And now imagine I can not only do that automatically with one model, I can do that with 10 different modeling algorithms and do it in an automated way and get kind of standardized output that I can compare one model to the other, comparing apples to apples. And I can even throw in here something that's called auto tuning. So I can not only look at one specific model for one modeling algorithm. If we take a decision tree, for instance, I can not set my parameters statically, but I can use the auto tuning to automatically find the best parameter setting for that specific model and that specific data set that I provide to that model. And I'll talk about that a little bit more in a second, what we mean by auto tuning and hyperparameter tuning. But in this case, basically all you need to do is create those three or set those three ingredients, your base table, your hyperparameters, and your assessment matrix, and let it run automatically. And we'll come back with 10, 20, 30 different models and you can easily identify which is the champion model. And then you can go one step further. You can not use static model searches, but dynamic model searches. And we call that model composing. And with that, we actually kind of looking across, you can call that the model space. So what are the potential models across all modeling algorithms, across all potential or possible hyperparameters, and which out of those millions and millions of combinations is the best one for your specific business problem that you're trying to address, and again come up with at the end with a champion model automatically. Obviously, there's a lot of compute power required for this. There's a lot of optimization going on in the background to make that happen, but this is a way of really automating the model search across a large potential number of candidates of models. So as I promised, a little bit more on automated hyperparameter tuning. What is an what is a hyperparameter? I guess most of you know that. If data science is your daily bread and butter work, that you have to certain parameters for the modeling algorithms that you need to tweak, and usually kind of you set a parameters combination, you run your model through, you look at the accuracy statistics of the model. You're not happy, you go back, you change the parameter settings, you run this again, and you go on like this for a while until you're happy with your settings. And what automated hyperparameter tuning is, help you to automate this process and make it more intelligent and more productive, if you want. And especially now with these new, more complex models that we're using these days for more complex business questions, like self-driving cars or natural language detection and chatbots, there's lots and lots of hyperparameters that you can, and that in most cases have to tune. And I often sometimes compare this. I spoke a little bit about the beginning of my career in the 90s, where we were working with decision trees and very simple neural networks and regression models. And tuning one of those models was a little bit like driving a car, where you have a number of certain instruments in your car, and you can easily watch them and manage them. You have your speedometer and you have your petrol gauge and things like that, and it's not too hard to understand what's going on. And I think tuning those more complex and more modern models, like the recurrent neural networks or computer vision models, it's like flying a plane. It's with so many parameters that you can tune, and that you kind of they interact with each other, and there's a connection or dependency between different parameter settings. So it's like in a plane where you have so many different instruments, very hard to control them and find the optimal setting. So that's where we're trying to help data scientists to make this tedious and often very iterative process easier and faster. And there's different approaches to doing this. One is the standard grid search, where we just use the certain points of certain combinations of parameter settings and create a grid. And then it's kind of a equidistant grid here that we're using, and then we hope that we have good luck, and that at those blue points you see in that diagram here on the left hand side, that's the best one of those points that we're checking is the best combination. Obviously we could be missing all the combinations in those cells, and the chances of finding the best one with that approach are a little bit limited. Another one is random search, where you don't have fixed points, but you randomly select these combinations, and the chances here to find your best model are a little bit higher. But the best optimal approach is what's called a Latin hypercube, where you have kind of a systematic variation of your parameters that's shown here on those distributions. But then you use random search of the combinations, and that gives you the highest chance of finding the optimal combination of your parameters. And that's what we are using in our automated optimized hyperparameter tuning, where we have an optimization algorithm running in the back, and that's going through all these different possible combinations, finding the best one, and checking the best one, and providing you with the best model in the least time that is available. Obviously, you can set your constraints of how many iterations you want to do, how much time you want to give that search, so that it doesn't take weeks. And also, it's good in this case because this is a large optimization problem that is to some extent independent in some areas. You can run different iterations in parallel, so having a kind of a parallel cluster that you can use for these kind of optimization tasks is also very helpful. And then another area that is a little bit overlooked sometimes in this whole machine learning pipeline is automated model documentation. As we all know, as data scientists, you need to present your results to someone to get a sign-off of whether this model that you created will be used to automate a decision process in the organization. And create these results and make them understandable for people that are not that deeply involved in predictive modeling or artificial intelligence is sometimes quite challenging. So again, you can automate that, and you can automate not only creating a visual report with graphics and numbers, but also you can automate the description of what you see in that report. So the notes that you see that reports here are get generated by natural language generation algorithms that create these descriptions of the reports automatically and make them easier understandable for users and decision makers. And then you can automate the whole thing. You can automate really the whole pipeline that was shown at the beginning. Just provide your table and just provide the constraints and the target, and all the whole machine pipeline is built automatically, and it provides you with a report or about which model works the best, but what should be a champion model, but maybe also what should be challenger models that are working quite as good as the champion model and should be not thrown away, but maybe used for champion challenger modeling approaches. And again, as I said in the beginning, this is not a black box. This is something that you can open and customize and improve with your own insights. I just want to show here quite a quick demonstration of an example of such an automated pipeline that could be built with automation tools. And what you see here basically is a web application, and all that's provided is a data source. In this case, we're looking at a child safety risk project, where we're looking at the risk maybe certain children are under in terms of their environment and so on. And we need to provide the data source and a target that we want to predict. And now everything is running in the background automatically, and you get some feedback here, what step of the pipeline is being processed. And this, as I said, is a web application, which means we're not only providing a graphical user interface for you to step through these automated processes, but also we're providing APIs, application programming interfaces, so that you can integrate these automated steps into your own applications. And that's what was done here. And you end up with a report, again, automatically generated, a report that tells you the gradient boosting is the champion model. We have a misclassification rate of about 9% with that model. We get a list of the most important variables that have been used in that model and the model accuracy. And obviously now you can open this. So I could open here my machine learning pipeline, go into the tool, and in a graphical user interface, if I want to, I can go and maybe try to improve and hit or beat that misclassification of rate of 9% that my automated algorithm has provided to me. And another area where you can apply automation is the explainability of a model. So make the black box transparent. That's becoming more and more important, especially with these very complex artificial intelligence modeling algorithms, the deep learning neural networks. You have to be able to open the black box that your auto machine learning algorithm provides to you, and not only at the surface to understand maybe what are the most important drivers of my model, but also going deeper. And especially in regulated industries like credit risk, credit management, sometimes these organizations need to defend a single prediction of their model. Why was a credit given to a certain person or not? Or why did I choose a certain interest rate for this specific person that applied for a loan? And though we need to be able to go down to one single prediction and identify how this prediction was created by the model. And that's what we mean by model explainability and model transparency. And also we have to make sure that the model is not biased and is complying to ethical standards against discrimination and other things. So all of that needs to be available to people that are using the model and not necessarily have built the model. So making this understandable and transparent is a big area where automation can help to make the models more transparent, but also more acceptable by users of the model at the end of the process. So bring this all together. We see the formula for success really with these three ingredients: the automation, which helps you to speed up the process and make the process faster. The second one is intelligence, which helps to make the process more accurate, to create more accurate models. And the third one is transparency, which helps to understand how this process actually worked and what the results of that process are that have been created. So where's auto machine learning headed from our perspective? I think the intelligence is still a big area for potential improvement, to integrate artificial intelligence into automated machine learning, so that you don't necessarily run your automation algorithm based on policies, on rules that you have set that are static, but based on dynamic search and analysis of the data that you're using for your model. I just mentioned explainability. That's very important, to create a white box that everybody can understand. And that's also editable. Not only that your machine learning, automated machine learning creates a nice model, but also that you be able to make it even better by going into the box and turn certain levers. And then the flexibility, cater to different levels of users. We see this in a lot of organizations, that there's different types of users. There's the programmers and the coders that use the code and write programs, and then there's the users that are a little bit more on the business side, that maybe want to use a graphical user interface, and other users want to use APIs to link into capabilities of automated machine learning. So catering to all these different levels of users is also an area where automated machine learning has a lot of potential to improve in the future. And for the second part, the shorter part of my presentation, I want to go back to this and say, okay, this is the part of the machine learning lifecycle, or the model lifecycle, if you want, that is concerned with the model development. How do we create a model out of our data and our algorithm that we can use for decision making? But this is not all. This is not, once I build a model as a data scientist, it's not the end of the story. This is actually the beginning of the story, because you need to be able to integrate that model into a decision process in your organization. Then, because the data doesn't change your organization, it's the decisions that change your organizations. And these decisions are by more and more organizations based on data analysis and not on subject judgments. And in order to do that, we have created a process model, and I won't go. Yeah, you have a question, Stefan? You're on mute, Stefan. Stefan, you're on mute. All right, sorry.
Thanks, Sasha. I refer to the slide, the 2 slides back, to the future of AutoML, where you mentioned explainability. Just a quick question from you, from your daily experience. Is it something, a subject which comes up from the client side as well? So do we really ask and say, hey, we need to be able to understand better how the model really works and what's happening inside of it?
Yes, it does. And it depends a little bit on the business application. It's less the case. I had this example at the beginning, where we're monitoring the quality of a production process. And there, it's obviously, you still want to understand what the drivers are. So you need to understand what's causing this specific issue right now, and how does the model actually work. But that's more from a person or an insider view. But as soon as it's about people, whether it be customers or suppliers or citizens, I mean, we have more and more smart city projects, where it's about how can we help, making life in a city better, and that also affects us as a citizen, not only as a customer. And wherever this is involved, you need to make sure there's no discrimination happening, and you need to understand if there's anything in the model that might lead to discriminating against a certain segment of the population. And also for regulators, often, especially in the finance area, that is very important. And we see this as well. I find this quite interesting with the self-driving cars. It's, I think the biggest issue right now that's stopping self-driving cars from hitting the road is the ethical issue, right? So this is it's becoming a big topic that we as humans need to understand how these models work. Otherwise, we won't trust them, right?
Yeah, I got 2 questions already from the audience. Ava, you asked what are the main challenges in AutoML. I would like to suggest to do that at the end. That
Okay.
would be the best. Roland has asked, how is the white box, which is here listed in the slide as well. How is the white box achieved if you consider neural nets and deep learning models where we don't really understand how the probabilities are distributed among the neurons? neurons?
Yeah, you can, especially with neural networks, we use kind of so-called proxy methods to identify. It's not down to the uh, lowest level, but it's kind of getting a more larger picture view of the model to understand how certain predictors are transversed through the model input and how they go through the neurons and what that actually means for the final outcome. And there, I also say there's a lot of work still to be done in this area to make neural networks more transparent, and to also to go deeper into this white box, if you want to open the box and go layer by layer, especially with the deep neural networks. But as I said, right now we're using proxy methods, and then also kind of, I would call them, in a lack of a better word, kind of brute force methods to identify how a special observation is created, for instance, in terms of, keeping 99 input variables constant and changing one and then seeing the impact on the result. These are all proxy methods where you don't go into the network itself and look at distributions, but you look at the impact of um, different variables, different predictors on the outcome, basically to identify what the impact is.
Thanks, Sasha. You can continue.
Okay. Yeah, so I said it kind of, this is our process model for the entire model lifecycle. We call it analytical decision lifecycle, where it's about analytical discovery on the left-hand side that I just talked about, which kind of maps to the machine learning pipelines. You have the different steps in there that you need to go through. And at the end of that part here on the left-hand side, you end up with one or several models that you then feed into what we call the deployment part of that lifecycle, where it's about registering, maybe making your model available to a central model database that you have available in your organization for governance and for later reuse. You deploy it into a business process, and then you use that model in the business application for decision making. And obviously, you want to capture the feedback from that decision making. Was the decision a good one or was it a bad one? And based on that, you then feed back into this deployment cycle where you monitor your model. You find out if your model is working well over time. And that's very important because analytical models have the property, if you don't touch them over time, they degrade. Their accuracy, their predictive power goes down. And in order to capture the time when something is happening and you need to intervene, which might be, you can do that on a constant basis every day, or you can do it on KPI, key performance indicator levels. If a certain accuracy threshold is not met anymore, then I need to go into retraining. And also these things, what I'm talking about, might be steps in the model lifecycle that could be automated as well. And I have a few ideas and suggestions here on the next slide, and you can obviously imagine that we're working on those and we have implemented a number of those already. So I talked about the data preparation already. I talked about the model development already, but here on the left-hand side, these are all areas that we're working on for the model deployment part. So once I have built my model, I can maybe push a button or trigger a process that automatically puts my model into my business application, into my business process. And then I have another process that is automatically triggered that looks if the model is degrading over time. And I have another process that is triggered maybe automatically or based on an expert looking at that outcome of the monitoring to say, okay, now I need to retrain that model. Let's go back and rerun our machine learning pipeline with new data now and create a new model and then put that back into our business process. So all these things can be automated and are sometimes a little bit overlooked these days, but will become more and more important in the near future with kind of, we see models really multiplying in businesses. There's so many different areas where you can apply predictive modeling, and more organizations I want to build more and more models to make sure that they can use that type of automation in their business processes. So I already talked about model ops a little bit. So basically that's what we call model ops, bringing the model into production and monitoring the model in production, and maybe even updating the model constantly that is in production. And again, this is an area where different types of user personas need to be involved in making it happen. The data scientist, the business unit that knows about the business process, the IT and operations that need to provide the infrastructure for the process to run on a mobile device, in my batch processes, on the web, and so on. So this is an area that is really high on the mind of our organizations that we're working with, to be able to automate this entire model lifecycle, not just the model development part of the pipeline. And to finish up, that's kind of our automated analytical lifecycle vision and architecture, if you want. So logical architecture, where you have different environments that are working together, very, very integrated, and you have different access points to those environments for the users. Might it be graphical user interfaces, might it be coding or API interfaces, and then you can automate all these different areas of this life cycle, of this loop here, and have checkpoints at those different steps of this loop to really industrialize your analytic life cycle in your organization and make it as automated as possible, keeping in mind at the same time that you always need to be able to go into this process at any time and make sure you have the governance and you have the insight, so not something runs out of control and you're losing money because nobody knows that your model is not predicting well anymore. That kind of checkpoint for the model monitoring, but also for the model development and other things. And with that, I think
how do you detect model drift?
Yeah, we do that with our monitoring capabilities. So we have here the performance analytical output, performance results, and they go back into our model management and continuously monitor if the model drifts or not over time using different statistical parameters. So we look at the input data, we look at the predictions of the model, and we compare that over time, and we compare it against the actuals to find out if the model is still predicting well or not. Okay, so I've got some information for you if you want to dig deeper. We have blogs out there. We have examples on GitHub that you can have a look at for our pipelines that we provide, and we have documentation. All our documentation is public now. It's online, so you can just go there, have a look, and you can even run a trial of our software if you want to, and see what kind of automation features we have there and play with them if you wish. And with that, I'm at the end and open for more questions if there are any.
Thank you, Sasha. Thanks for the talk. Can you go back 2 slides, but we have with one kind of overview. Now again, thank you very much. So one just organizational question, which was asked in the beginning. We will get your presentation.
Sure.
So everyone who's just participating, don't worry. I'm going to upload it to the YouTube channel of AI Swiss. And I guess it will be there on Friday latest. So we should be ready by then. So coming back to the questions which came up also during your presentation. One was just raised by Ava. Ava, did you have you joined us? Can you hear me?
Yes, I can hear you.
Hi. So you had a question, I said, which will be asking at the end. What was your question?
So what are the main challenges in AutoML, and can we basically use it for all of the problems, or is it more limited to a well-defined class of problems?
Yeah, so I'll start with the second part, the types of problems. I think it can be applied to predictive modeling. I mean, there's lots of other types of statistical analysis and data analysis out there, but the automated machine learning really focuses on predictive modeling. So you need a target in your data. You need to want to predict something from the day with the data that you have, and there I think it's also a little bit more targeted towards classification problems. So in lots of customer relationship management problems, we have this classical event modeling. So does the customer respond to my offer? Does the customer buy something? How likely is the customer to return a product? How likely is the customer to cancel the service? That kind of thing. And there is kind of binary event might be kind of a nominal event as well, but that kind of classification problem is where automated machine learning works, from my experience, the best. That doesn't mean you cannot apply it to traditional prediction modeling, where you have an interval target, where you might want to predict what's the default outstanding debt of a loan customer in the next 5 years or something like that. But that's the traditional classification model is the more targeted area for automated machine learning, from my experience. And the first one, what are the challenges? I hope I could address a few of the challenges in my talk, but it's basically going, maybe what I see today, going from a policy-based automation where I have certain rules, and these rules are kind of checked when I run my automation. So is my model accurate enough? I have to set a threshold, maybe 90% or 10% misclassification rate, 90% accurate classification is my threshold. Is it the Kolmogorov-Smirnov statistic has to have a certain value, that kind of thing. Lots of other thresholds I can set, but these would be static rules. Going more towards artificial intelligence based automation, where I have an algorithm running in the background that looks at the data, that analyzes data, makes suggestions maybe of what I should do, what I can do, what would be a more kind of in terms of reinforcement learning, what would be a potential valuable strategy I could follow in my machine learning pipeline to build the optimal model at the end, and getting that kind of guidance during my automation process, other than just running it as a black box with no interference from a human perspective in general. Does that answer your question?
Yes, it does. Thank you.
Thank you.
Thanks for asking, Ava, for coming up with the question. Just to sum it up again, maybe you can give a summary regarding my next question. If you think of automation sometimes sounds like I give up my control, right? And so looking at giving up control and the freedom of having speed, do you think are there specific areas where you say automation makes perfectly sense and where you shouldn't be afraid of losing control? How much control do we have over the automation?
Yeah, I mean, that's what I mean by white box, basically, what you're saying. And obviously one area is, and that kind of it's common sense, right? You need to have checkpoints in your automation. And we're trying to provide these checkpoints. So you say, okay, at this point, I expect this from the automation. And if I don't get that from the automation, then I can go in and see what maybe the automation will provide me with some information about what has gone wrong, where areas are that are not performing as well as I thought they would. And that's why my checkpoint has not been met, basically. And then also being able to interact with the automation and open it up and say, hey, this is an area where and when we're doing this with optimization today, this is an area where I want you to automate, but in the other areas I want to keep control. So being able to really customize my interaction with that automation algorithm to say, do automation here, but here's about where I want to do my own work, right? Or kind of maybe get some guidance from the automation, but not let's let the automation run all by itself, basically.
Ella had a question as well. Ella, you are allowed to speak. Do you want to ask?
Thank you. So I'm looking at this wonderful slide,
right?
And it looks really cool and impressive. But since I'm a hacker, I would like to know how far is this automated? So what is the actual stand of things at the moment? And with relation to this slide?
In relation to this slide, it's basically all automated with the push of a button right now.
Oh, okay.
So it's not. I mean, it can be if you and your organization wanted to run this all automatically, you could. So we as I said, we provide user interfaces and we provide APIs. You can run, and I try to show that in the web application. You can run all this automatically. maybe you shouldn't, as we just talked about. Maybe you should have certain checkpoints. And that's why we, and also we have interfaces where you can push buttons to say, okay, I run my model in my model development environment. I found the best one, it's ready, push a button, and it goes to what we call the managing and monitoring environment. And there you might have another checkpoint, you might have another person looking at it, and this person can push a button again, it goes out to what we call the analytic execution environment. And this can all be, it can be automated, and we don't provide the automation out of the box, but we work with organizations to meet their automation requirements, if you will.
Okay, thank you very much. That was cool.
Thank you.
Thanks, Ella, for the question. I think it was a good question as well. Just a look from a business side. Do you have any kind of benchmarks or something like that where we can see, oh, when you use automation, you have gains in time or something like that?
Yeah, it's a little bit hard to tell. I mean, we see improvements in productivity, that's for sure, but more from a perspective of saying we're giving the human a head start right now. And I haven't seen an organization yet that, going back to the previous question, that has automated this entire process without human intervention. They all say, okay, we do certain parts and then we have somebody checking, and then we do another part and we have somebody checking. And now I lost the question. What was the question? Sorry.
I was just asking regarding the benchmark. Is there any kind of
benchmark? Correct. So what I was trying to say was, it's a little bit difficult. Obviously, I could run this algorithm and say, okay, if I run this algorithm, this automated pipeline, it runs through in 2 minutes. If I let a data scientist work on it, he might need 2 hours or 2 days. But it's a totally different approach, right? And so it's kind of more, as I said, it's kind of more supporting the data scientist to become faster and more productive, rather than having an algorithm that runs as fast. And there's also a methodology out there that comes from the data engineering, the data science engineering side, which is called DevOps, which is the process of putting an application into production as fast as possible. And there you can easier judge the time gains or improvements that you get, because you don't have that, the application either works or it doesn't, right? With analytics, it's not that easy. It's not a black-white decision. It's, the model can be really bad and it can be in production really fast, but that's not good. It might take a little bit longer, but then you get a model that is good and goes into production. So that's kind of your bandwidth that you have to work with. So it's a little bit hard to judge what the time improvement is, the performance improvement, but it definitely helps make data scientists faster.
Thanks, Sasha. Roland also just had a question. Roland, you can speak.
Yeah, good question. So does your product or SaaS also offer some kind of no-code or low-code model development?
Yes, it does. That's what I mean by the user interfaces, where you can work in a graphical environment and you don't have to code at all. And then the nice feature of that as well is that you get the code in the background. So you can always switch from building your code in a visual environment and then extracting the code that is generated in your machine pipeline and put it into an automated process. Or you can use the APIs or code to run it from a programming interface.
So you can start as a no code or low code and then continue basically fine tuning it by using the generated code.
Yes, you could do that. Yep.
Yeah. Okay, thanks.
Awesome. Thanks, Roland, for bringing up the question. It's also very helpful. Manuel, who helped us to set up a presentation at the beginning, also has a question. Manuel, you are allowed to speak.
Yeah, thank you, Stefan.
Thank you.
So where do you see the most set of use cases with regards to AutoML and enterprise customers? Is it with classification or regression or audio or video or image-based use cases? Because the way the data is collected, the way the data is pre-processed, and the way explainability is done, and also model deployment, these are very diverse with regards to these kind of use cases. And of course, which essentially calls for a more robust system. Sometimes we are also talking about edge-based deployment, the deployment of the models on the devices. So
Yep.
Where do you see in the context of enterprise customers?
When you talk about the business applications, basically.
Yeah, exactly.
Yeah. I mean, it's right now, it's mostly in the area of classification models, what we see. So, but there's a diverse area of classification models out there. It's a big area of customer, we call customer intelligence. So understanding the customer better and providing more personalized, targeted services and offers and products to customers, making recommendations, that kind of thing. And then there's the classification modeling for manufacturing process, process monitoring, basically. I had one of these examples in the beginning. So a lot of manufacturers are now getting sensors from their manufacturing process, but also using computer vision, so images that they take from certain steps of the production process, and then it's basically a classification model to identify whether the product that is being produced is correct or not. So we're seeing there automation going on, as well as in a little bit less extent in the finance areas, with kind of credit management, portfolio management, that kind of thing. Especially with the credit management, money lending in general, there's a lot of regulations, and so you need to be able to put a lot more checkpoints into your automation process if you want to use that. So they're not that far yet. Yeah.
Thank you.
Yeah, thanks. Thanks again, Manuel, also for the help in the beginning,
klar.
for good questions.
Bist du am Zahlen von dem Relais? Aha, weil ich wollte das.
Okay, so thanks again. I think we're pretty much at the end of today's meetup. I want to say thank you for the audience for the awesome questions you had again. It was fantastic to have you here to join us. I want to say thank you to Sasha, who did a really pretty good job in explaining and giving us such insights into what AutoML is and how the things can be automated. And happy to see you all next time again in November the 25th. Thanks again for being part of it, and hope to see you again, sometimes in person again when Corona is over. Please stay safe and hope we see each other again. Bye, guys.
Thank you very much. Bye-bye.
Thank you. Bye-bye.